Our discussion of modern physics is now going to continue past quantum and atomic physics and now focus on what is arguably one of the most relevant topics of the past 100 years, nuclear physics. Specifically, what is going on inside the nuclei of atoms and where that can lead us in a bunch of different ways. And today we're going to be specifically focusing on a concept known as binding energy. But before we start talking about the specifics of binding energy, it's important to get down some basic terminology and labeling and lingo that's very, very common in nuclear physics, so we can make sure that we understand everything from the base up. And let's start with this idea of nucleons. Well, what is a nucleon? A nucleon is a particle that is located inside the nucleus. It's what the nucleus is made out of. And I know that you all know the two types of nucleons, but let's focus on some of the specifics. The first is known as protons, that we label with is a capital Z is the number of protons, and this is known as the atomic number. And that atomic number determines the specific element that a particular atom is. So for instance, if we have one proton, then I would have an atomic number of 1, and the element for that atom would be hydrogen. If we have 6 protons, so an atomic number of 6, that would be an atom of carbon, etc. Now, the mass of a proton is 1.0073 U. And what is a U here? A U is what is known as a unified atomic mass unit. So 1 U is equal to 1.66 times 10 to the negative 27 kilograms. Finish my parentheses there. Now that, as we can see, really we just use U because we have so much scientific notation with the masses of these particles. They're so tiny that just this allows us to have a nice, simple way of visualizing how many nucleons we have. One proton, and we'll see in just a second, one neutron are pretty close to 1 U, but they're not exactly that. And the charge of a proton is positive of the elementary charge, so that's positive 1.6 times 10 to the negative 19 coulombs. Now, the second type of nucleon are, of course, neutrons, and the neutron number is the number of neutrons, which we abbreviate with a capital N, and the mass of a neutron is 1.0087 U, slightly bigger than a proton, not much, and its charge, though, is 0. It has no charge at all, and so therefore does not experience the electric force. It doesn't get attracted or repelled from protons and electrons, etc. Now, the number of neutrons determines the isotope a specific atom is. Now, before we get into isotope, let's bring up one more term here, which is that if we add the atomic number and the neutron number together, so if we add the number of protons and the number of neutrons together, we get something that we abbreviate with a capital A, which is the mass number, which essentially is really just telling us the nucleon number, the number of nucleons that there are, protons and neutrons combined. Now, the reason why this is important to know is that when we talk about isotopes, so first off, number of protons gives us the element, number of neutrons gives us the isotopes, but when we talk about isotopes, we really refer to the mass number, not the neutron number. So for instance, let's say we have an atom of carbon once again, so that would have 6 protons automatically, and if we had, for instance, 8 neutrons, well, 6 plus 8 is 14, so the specific isotope would be carbon-14. If I have 6 protons and 6 neutrons, that would be carbon again, but now I would have a mass number of 6 plus 6 is 12, so that would be an isotope known as carbon-12. They behave very similar, carbon-12 and 14. In fact, they can be substituted in for each other in most chemical processes, but we're going to learn that there are some key differences down the line. Now, when we're labeling isotopes and these nuclei in general, we use this convention here where we write the chemical symbol in the middle, and then in the upper left corner, we put the mass number, the bottom left corner, we put the atomic number, and then the upper right corner, we put the charge. Now, I've just put positive or negative here. It could be positive, negative could be positive 2, minus 3, whatever. And that's really telling us if it's an ion, for instance. And let's look at this particular atom here to kind of make sure we understand all of this. So looking at this particular atom that I've drawn a picture of, we have 3 protons. If we look on the periodic table, 3 protons, so an atomic number of 3, corresponds to the lithium, which is the chemical symbol Li. And I'm going to go ahead and write the atomic number down immediately. And now I'm going to count, let's see, the number of electrons, and I see I have 4 electrons here. Well, if I have 3 protons and 4 electrons, that means I have 1 extra negative charge, so it's going to have a minus sign in the upper right corner, so this is actually an ion. And then lastly, I'm going to count the number of neutrons. The number of neutrons I have here is 4, But remember, I don't write the number of neutrons here, I write the mass number, so 3 plus 4 would be 7, and this isotope would be specifically lithium-7, and that's how we say it. If I say I want to refer to this nucleus, I would say it's a it's an atom of lithium-7. Alright, so let's look at another nucleus, and we're going to really not focus on the electrons now. Most of this unit, it's all nuclear stuff, so the electrons are not going to be nearly as important. We're going to focus much more on the nucleons. And this is a nucleus of helium-4, meaning that I've got 2 protons and 2 neutrons, so combined they have a mass number of 4. And my question is, okay, what is the mass of this nucleus? Well, we could do some pretty easy arithmetic here, and I could say, all right, well, if it is 4 nucleons, I've got 2 protons, 2 neutrons, so to find the mass of the nucleus, all right, well, let me just find the mass of the nucleons. And I will just add together 2 times the mass of the proton plus 2 times the mass of the neutron. And let me go ahead and do that with the numbers I had on the previous page. I'm going to go ahead and stick with the atomic mass units rather than kilograms to avoid all the scientific notation. So 2 times 1.0073 U plus 2 times 1.0087 U for the neutrons gives us a total mass of this nucleus of 4.0320 U. So that's the mass of all the nucleons that make up the nucleus. And we might think, okay, we're done, right? That's it. But not quite. Because if we end up actually measuring the mass of this nucleus, we actually discover that the mass is 4.0026 U, so 4.0026 atomic mass units. This might raise some red flags, because what exactly happened here? Why are these not the same number? Shouldn't it, this is basic addition here. I'm just adding the mass of 2 protons, 2 neutrons together. Shouldn't that give me the mass of the nucleus? And specifically, the mass went down. Where did we lose this approximately 0.03 U? Where did that go? Well, where it went is something known as nuclear binding energy. Now, nuclear binding energy really has 2 different definitions that work in tandem, but it's 2 different ways to visualize it. One, it is the energy released when nucleons come together and bind into a nucleus. So in other words, if I have these 4 nucleons here, they come together and bind into a nucleus, and energy is released. So part of the mass of these individual nucleons, part of the mass of each one, is literally converted to energy. And this is the nuclear binding energy, that energy that is released when they bind. Now, what type of energy is that? Well, one, it could either be the kinetic energy of the nucleus, basically the nuclei that are created could be moving around, so there could be that. And it also can be often released as electromagnetic radiation, oftentimes gamma rays. Those are really, really high energy photons, really, really high energy light. Another way to visualize this is that nuclear binding energy is the energy required to pull apart a nucleus into what are known as its constituent nucleons, aka into the protons and neutrons that make it up. So if I have a nucleus, if I want to separate all of these protons and neutrons away from each other, I have to put in an amount of energy equal to the nuclear binding energy into the system to get them separated out. And that energy is literally added to the mass of the nucleons. Each proton and neutron that's separated gains some energy and converts it to mass. And so those masses go up. Now, hopefully by this point, there's probably been at least 1, if not 2, big red flags about this whole concept. Which is first, what? Because mass and energy are 2 different things. Why am I talking about mass becoming energy and energy becoming mass? Well, the thing is that they are actually flip sides of the same coin. In 1905, Albert Einstein, when he published his special theory of relativity, one of the things that he derived from that was that mass and energy are really not separate entities. In fact, it was discovered in these papers that, all right, if we have a mass that has no mechanical energy, so in other words, it's not moving around with kinetic energy, it is not in sort of a system with potential energy, it doesn't have any thermal energy, well, it still has energy. It actually has an intrinsic amount of energy just by nature of its existence. That mass has some amount of energy intrinsic to it. And that mass can be converted to that energy, or that energy can therefore be congealed into this mass. In fact, we now know we have to rewrite a law we've learned in either chemistry or in AP Physics 1, which is that law of conservation of mass and the law of conservation of energy can no longer be treated separately. Energy can become mass, and mass can become energy, so individually they're actually not a fully complete picture. Instead, now what we have is the law of conservation of mass energy. And that will basically say, okay, whatever the mass is, some of it can become energy, whatever, but that whole mass energy system, that's conserved. But the individual pieces of mass and energy, they may not be. And this idea of mass energy equivalence brings us to what is unquestionably the most famous equation in all of physics. E naught is equal to mc squared. Now, what does that not mean? That's because this is the rest energy of a piece of mass. Because if that mass is moving around, it's going to have some additional energy, like kinetic energy and things like that. This is specifically saying the energy intrinsic to that mass. That when it's at rest, this is the energy it just possesses. And that is going to be equal to mass, and then times the speed of light in a vacuum squared, where obviously that is 3 times 10 to the 8th meters per second. Now you'll notice I didn't write units on the energy and the mass here, and that's because there's a couple of different ways we can do this. One is if we want the energy in joules, then we need to have the mass in kilograms. However, another way we will often do this is we will actually often see the mass written in values of mega electron volts per c squared. I know that sounds weird. This is very, very common in nuclear and particle physics. And when we multiply that by c squared, then the c squareds will cancel out, and we will get an energy in mega electron volts. So the reason why we do this is because of the fact that joules are way too big here. Mega electron volts and electron volts in general are just much more what we want to go with. And so this allows us to do some quick, easy mass to energy conversions without having to do a bunch of extra math. Now, one atomic mass unit, or 1 U, is equal to 931 mega electron volts per c squared. Now, quick note, remember mega means times 10 to the 6. Now, taking this a step further, how could we apply this to the nuclear binding energy concept? Well, if I want the nuclear binding energy, that amount of energy is going to equal to delta M times c squared, where delta M is what is known as the mass defect. And that is the difference in mass between the nucleus and the sum of the individual nucleon masses that it composes. So for instance, if I have an atom of carbon-12, its nucleus will have some mass, and that's composed of 6 protons and 6 neutrons, so the sum of its nucleon masses, so that would be 6 times the mass of the proton plus 6 times the mass of the neutron, will have a different mass. The difference in these two values is known as the mass defect. So if we multiply that by c squared, we know how much energy is either released or gained by the nucleus as it is formed or broken apart. So let's go back to this example. So we already got the mass of the nucleus for helium-4, and we already had calculated the mass for the individual nucleons. And let's say we want to know either the energy that is absorbed by the nucleons as they're pulled apart, or the energy that is released when we put all these into the nucleus and that mass is converted to energy. So let's first calculate, the mass defect, and that's just going to be the difference in these two values. And that specifically comes out to be 0.0294 U. And I'm going to go ahead and tell you, a lot of times we're going to have longer decimals than usual here because we're dealing with very, very tiny numbers. That's okay. We have to be really precise in this unit. Okay, so we got 0.0294 U. And now, to figure out the nuclear binding energy, there's two different approaches we could take. The first is I'm going to use E is equal to delta M times c squared. Now I'm going to convert this mass defect into kilograms by remembering that 1 U is 1.66 times 10 to the negative 27 kilograms. So I multiply those together, and I get a mass defect of 4.88 times 10 to the negative 29 kilograms. And now I stick this into the equation for the nuclear binding energy, so I'm going to multiply it by c squared, and I get 4.39 times 10 to the negative 12 joules. That is the nuclear binding energy for this particular nucleus, the amount that is either released when it forms and the amount that it absorbs when they're split apart. However, there's a second way I could have gone about this that would have actually have made the math even easier. Instead of converting this mass defect to joules, I'm going to convert it to mega electron volts per c squared. So I'm going to say, all right, I'm going to take this U value and multiply it by 931, because 1 U is equal to 931 mega electron volts per c squared, and we get 27.37 mega electron volts per c squared. I stick this now into my nuclear binding energy equation, and well, these c squareds just cancel, and I have, oh, look, I'm done. 27.37 mega electron volts. So 27.37 times 10 to the 6 electron volts. And if I convert that to joules, I will find out that that is 4.38 times 10 to the minus 12 joules. Now this is slightly different from the last value we calculated. The last value was 4.39, but considering that we are rounding off a lot of things to just a couple of decimal places, that is not that surprising. This would still be an acceptable calculation. The other red flag that might have popped up though was, why is it taking energy to pull the nucleons apart, and why is it releasing energy to push them together? Because if we look at our nucleus, particularly this is for helium-4, I've got 2 protons and 2 neutrons, and the neutrons don't really do anything here, but the protons, they're exerting electric forces on each other, and those electric forces are going to be pretty darn big because they are very, very, very close to each other. And we know the electric force is pretty strong comparatively speaking. So why is this nucleus not just blowing apart into pieces? Why is it taking energy to pull it apart? And that's because we are ignoring a very, very crucial force here that we've not discussed yet in this course, which is that of the strong force, often known as the nuclear strong force. The strong force is a fundamental force that only exists between quarks. So remember, first off, what are quarks? Quarks are these pieces of matter that, one, can't exist by themselves and always exist within, for instance, nucleons like protons and neutrons, or they can exist in these more exotic particles known as mesons. But the thing is, though, is that the strong force, only quarks experience the strong force. Electrons don't, neutrinos don't, which we'll learn more about later. And the thing is, so this strong force binds the quarks into these nucleons. So if I have a proton or a neutron, the strong force is what's keeping the quarks together. But it also binds these nucleons together. Because if I have a proton and a neutron and another proton all right here, those quarks are really close to each other and they're exerting this strong force on each other. Now when I say this is a fundamental force, that means I've got, gravity, I've got the electric force. This is its own separate category from those. So we know that the strong force is what's holding these together. Why isn't it not that the strong force is always dominating the electric force? Like if I separate these protons, why doesn't the strong force just pull them right back together? And that's because the strong force is actually only apparent at extremely, extremely small distances. And by small distances, I mean, and basically the maximum range is about 3 what are known as femtometers, FM here, where a femtometer is 1 times 10 to the negative 15 meters. So the strong force only really exists between 2 particles if they are within 3 femtometers of each other. And to keep in mind on how tiny this is, a regular atomic nucleus, the smallest one, has a diameter of about 1.5 femtometers, and the maximum size is 15 femtometers. So already right here, we're, getting to a point where this is going to be a couple of femtometers across. We're already experiencing, the strong force is very apparent here, but as soon as we pull these a little bit apart, the strong force just vanishes. It becomes really close to zero and the electric force dominates. But when we bring these protons really close together, we're having to use a lot of energy. But when they get real close, that strong force kicks in and really quickly glues them together, makes them into a cohesive nucleus. So we have to take energy to overcome this strong force. So what are our takeaways on this lesson on binding energy? Well, one, can we properly identify and label isotopes if we know like their atomic number and mass number, etc.? And in turn, can we determine the number of nucleons, protons, and neutrons present in a named isotope or a labeled isotope? Can we calculate the binding energy of a specific atomic nucleus, finding first the mass defect and then using delta M times C squared is equal to that energy? And can we determine if that energy is lost or gained by a nucleus in a specific scenario? Keeping in mind that if we add nucleons together, if we push them together, energy is released because some of the mass of those nucleons gets converted into this nuclear binding energy. And if we pull the nucleons apart, we pull the nucleus apart, I should say, well then we are adding energy to it, and that energy is becoming more mass in the individual nucleons.